Something is stirring along one of the least visible boundaries on the entire planet, and scientists monitoring it right now say they haven't seen this many warning signs light up across this stretch of ocean floor at the same time in years. Beneath the Atlantic, along a chain of volcanic islands stretching from the edge of the Arctic Circle down toward North Africa, magma is on the move in at least 3 separate locations simultaneously. And researchers tracking each one say the timing of this overlap is exactly what's keeping them glued to their monitoring screens. Today, we're going to break down where this activity is happening, what's actually moving beneath the surface at each site, and why scientists studying this region say a quiet-looking ocean can be hiding some of the most active geology anywhere on Earth. Let's start with the feature running underneath all of this, because almost nobody realizes it's there. Splitting the Atlantic Ocean floor, roughly down the middle, running from north of Iceland all the way south past the equator, sits the Mid-Atlantic Ridge, an underwater mountain chain that marks the boundary where 2 tectonic plates are slowly pulling apart from each other. As those plates separate, molten rock rises up from deep within the Earth to fill the gap, cooling into new ocean floor and, in a handful of places, actually breaking the surface as land. Iceland is the most famous example, an entire island built directly on top of this splitting boundary. Further south, the Azores and the Canary Islands sit near this same volcanically restless province, shaped by related plumes of rising magma, even though their tectonic setting is slightly more complex than Iceland's. Clean, divergent boundary. All 3 regions share one thing in common. They sit directly above places where the Earth's crust is thin, stretched, and constantly being fed by magma pushing up from below. Here's what makes this stretch of ocean floor genuinely unusual right now. At the northern end of this chain, on Iceland's Reykjanes Peninsula, the Icelandic Meteorological Office has been tracking a volcanic system called Svartsengi that's currently holding more accumulated magma between eruptions than at any point since the current eruption sequence began back in December of 2023. As of the most recent measurements, model calculations put the accumulated volume beneath Svartsengi at roughly 27.5 million cubic meters, with the ground above it still rising at a rate of about 2 centimeters every month. That might not sound dramatic on its own, but consider that this current pause without an eruption is already the longest stretch recorded in this entire eruption series, and officials have explicitly warned that because there's now more magma stored underground than during any previous lull, if it does eventually break through to the surface, the resulting eruption could be larger than any of the ones that came before it. Think about what that actually means happening beneath your feet if you were standing on that peninsula. A slow, steady swelling of the ground, invisible without precise satellite and GPS measurements, building month after month as an underground reservoir the size of tens of millions of cubic meters continues to fill. The Icelandic Meteorological Office's hazard assessment for the area remains at a heightened alert level, and their most likely scenario going forward is still a magma intrusion racing toward the surface along the Sundanukur crater row, the same fissure system responsible for the string of eruptions this region has already seen since the cycle began. Warning time before an eruption in this kind of system can be as short as 20 minutes. To put that pattern in historical context, Svartsengi has a documented eruption history stretching back to the year 1179, with at least 12 recorded eruptions since then, meaning it has erupted, on average, roughly once every 71 years across recorded history. What makes the current cycle notable isn't just the size of the magma reservoir, it's the frequency. This system has already produced multiple eruptions since December of 2023 alone, a pace far faster than its long-term historical average, which is part of why researchers are treating each new lull as a genuine open question, rather than a return to dormancy. There's also real-world stakes tied to how this plays out. Iceland sits directly beneath some of the busiest transatlantic flight corridors on the planet, and volcanic ash from a much smaller Icelandic eruption back in 2010 famously grounded flights across Europe for the better part of a week. Nothing currently observed at Svartsengi points toward that scale of disruption, since this system tends to produce relatively low ash-poor fissure eruptions rather than the explosive, ice-capped eruption that caused the 2010 shutdown, but it's part of why aviation authorities keep a standing alert level tied to this specific volcanic system at all times. If you're finding this breakdown useful, go ahead and hit that like button. It genuinely helps this kind of science coverage reach more people who are curious about what's actually happening beneath our feet. Now travel roughly 1,000 miles south, out into the mid-Atlantic itself, to the Azores archipelago, and you'll find one of the most revealing case studies scientists have ever assembled on exactly how magma can move without anyone noticing until it's almost too late. Back in 2022, thousands of earthquakes suddenly rattled the island of São Jorge, and a study published this year, using roughly 18,000 precisely relocated earthquakes recorded by both onshore and ocean bottom seismometers, finally revealed what had actually happened underground. An enormous body of magma, enough to fill somewhere around 32,000 Olympic-sized swimming pools, had surged upward from more than 20 kilometers beneath the island, racing toward the surface, before finally stalling out at a depth of just 1.6 kilometers, narrowly avoiding a full eruption. Researchers who led the study called it a stealth intrusion because most of that dramatic rise happened with remarkably little seismic activity to signal what was going on. It was only after the magma stopped moving and got trapped against a crustal fault that the earthquake swarm most people actually heard about finally began. That distinction matters enormously for how scientists think about hazard forecasting in this entire region. If the most dangerous phase of a magma intrusion, the rapid ascent, itself can happen almost silently, then earthquake swarms that show up afterward aren't necessarily an early warning sign at all. They might be the tail end of a process that already reached its most critical point underground before anyone on the surface felt a thing. That's precisely why researchers studying the Azores describe this triple junction, a spot where three tectonic plates meet in an unusually complex arrangement, as something close to a natural laboratory for understanding how magma actually interacts with crustal faults on its way toward the surface. Lessons that apply directly to every other volcanic island sitting along this same broader Atlantic province. Further south still, in the Canary Islands, a third and separate story has been quietly unfolding beneath Tenerife. Since the middle of June this year, the Canary Islands Seismic Network has recorded a sharp uptick in activity beneath the southwestern sector of the Las Cañadas caldera, with more than 200 low-magnitude earthquakes detected in a single 48-hour stretch at depths of roughly 10 kilometers. Scientists interpret this pattern as pressurization of the island's volcanic and hydrothermal system, driven by magmatic fluids being injected from below, and it's showing up alongside elevated carbon dioxide emissions in the area around tide and measurable ground deformation that's been building since 2024. It's worth being clear here that this activity is consistent. With a pattern of recurring unrest, researchers have tracked on Tenerife going all the way back to 2016 and 2017, and current observations do not indicate any increased likelihood of an eruption in the short or medium term. This isn't a system on the verge of blowing, it's a system scientists are watching precisely because this kind of running low-level unrest is exactly what a slowly pressurizing magma reservoir tends to look like from the outside. Tenerife carries its own set of real-world stakes too. Mount Tide, the volcano at the heart of this caldera, is the highest peak in Spain and one of the most visited natural landmarks in Europe, drawing millions of tourists to the island every single year. That combination, a genuinely active volcanic system sitting directly beneath a major tourist destination, is exactly why Spanish and Canary Islands authorities maintain a dense, permanent monitoring network across Tenerife, rather than treating this as a remote, low-priority site the way a truly uninhabited seamount might be treated elsewhere. Bring these three locations together, and a pattern starts to emerge that's bigger than any single island. Record magma accumulation beneath Iceland's Reykjanes Peninsula, a freshly published deep dive into a stealth magma surge that nearly erupted beneath the Azores, and an active, ongoing swarm of pressurization earthquakes beneath one of the Canary Islands' most iconic volcanic calderas. Three separate volcanic provinces spread across roughly 2,500 miles of the same broader Atlantic tectonic setting, all showing genuine signs of magma actively pushing upward at the same time. Individually, none of these would necessarily make headlines. Together, they're exactly the kind of overlapping pattern that makes researchers sit up and start comparing notes across institutions and borders. If deep Earth science coverage like this is something you want more of, subscribing means you'll catch the next update the moment any of these systems shows a meaningful change. There's a broader reason scientists are able to see all of this happening at once in the first place, and it comes down to how dramatically monitoring technology in this region has improved. Ocean bottom seismometers, the kind used to help relocate those 18,000 earthquakes in the Azores study, allow researchers to detect activity happening directly beneath the seafloor, rather than relying purely on instruments positioned on land, which historically missed a huge amount of offshore seismic activity entirely. Combine that with satellite-based INSAR measurements capable of detecting ground continuous GNSS stations, tracking the exact position of the ground in real time, and researchers today have a genuinely unprecedented window into slow-motion processes that used to remain completely invisible until an eruption was already underway. That's part of why this moment feels different. It's not necessarily that the Atlantic's volcanic systems are more active than they've been historically. It's that scientists can finally watch several of them closely enough, simultaneously, to notice when they start moving together. To be clear, nobody studying any of these three systems is forecasting an imminent eruption at all of them, or even at any one of them specifically. Volcanic unrest, even genuinely significant unrest like record magma, accumulation or sudden earthquake. Swarm resolves without eruption far more often than it ends in one. It's also worth directly addressing the kind of exaggerated claims that tend to spread whenever headlines mention magma and the Atlantic in the same sentence. Nothing in this data suggests a hidden supervolcano, a sunken continent stirring back to life, or any single connected magma system spanning the entire ocean. These are three separate, well-documented volcanic provinces sitting along a shared tectonic boundary, behaving the way volcanic provinces on active plate boundaries regularly do, just happening to show meaningful activity within the same stretch of months. What ties this story together isn't inevitability, and it isn't some hidden mega structure waking up beneath the seafloor. It's a tension. Researchers across Iceland, the Azores, and the Canary Islands are exchanging data, comparing deformation patterns, and treating this stretch of the Atlantic as a single interconnected natural laboratory rather than three unrelated island chains that happen to share an ocean. Bringing this all together, the Atlantic has always carried an image of stillness in the public imagination, a vast, calm expanse separating continents rather than a place where anything is actively happening underground. What's unfolding beneath? Iceland, the Azores, and the Canary Islands right now tells a very different story. One of magma quietly climbing toward the surface in multiple places at once, sometimes announcing itself with thousands of earthquakes, and sometimes rising almost silently until it's already nearly there. Each of these three systems will likely be resolved on its own timeline, through its own local monitoring network, and possibly without any eruption at all. But the fact that researchers studying three separate volcanic provinces along the same broad tectonic boundary are all watching genuinely elevated activity in the same stretch of months is precisely the kind of coincidence or pattern that serious Earth scientists don't simply shrug off. Nothing here demands panic, but everything here demands attention, and that's exactly why scientists monitoring this stretch of ocean floor say they simply cannot look away right now.